Alright, you crazy kids, here's your lecture on the activity series and electrochemical cells. So a long time ago, we used the activity series to predict whether or not a single replacement reaction would occur. And we just said that they switch places or something like that. In reality, it's a little bit more in depth. So the activity series relates to an element's ability to lose electrons. Specifically, elements in the series lose electrons to the positively charged ions of any element below them. When we did single replacement reactions, you have to recur, I said, oh, the compounds are always in solution. Well, this is why. So it's all about an electron transfer, or a redox reaction. The more distance between the components on the activity series, the more likely that redox reaction will occur. We're going to use that information when we talk about electrochemical cells. If I had a redox reaction, something like a single replacement, maybe hydrochloric acid and zinc, and I were to just throw some zinc and some hydrochloric acid, those two components are in contact with each other. Because they're in contact with each other, we have a lot of heat or energy that accompany the electron transfer. If I separate the substances and connect them with a wire, I no longer have heat being given off. Instead, the electron transfer is accompanied by a transfer of electrical energy. We call that electricity, the flow of electrons. We're going to be talking about galvanic or voltaic cells, two words for the same thing, where you're dealing with chemical energy being converted into electrical energy. Let's take a look at what that looks like. This is the setup for a standard galvanic cell or voltaic cell. You have an electrode, in this case we have some zinc. You have another electrode, some nickel. They're in ions of their own solution. The anion component of this actually doesn't matter. It's going to be no change in its oxidation number, or it's going to just be a spectator. It's still present in the solution, but the identity of it doesn't really matter. We'll talk about why in a minute. If I were to set up this in lab and hook it up to a battery, believe it or not, well, not hook it up to a battery, hook it up to a light bulb, this is a light bulb, that light bulb would just seem to be randomly turning on. But in reality, it's because of a redox reaction. Let's talk about why. We have zinc. We have nickel. We have nickel ions and zinc ions. What I just talked to you about in terms of the activity series is when you have something that's in contact with the metal ions of something below it, a redox reaction is most likely to occur. Here I have zinc in contact with a metal ion solution that's below it on the activity series. That means this zinc is going to be losing electrons to those nickel ions. I'm going to show you how that looks. Here's a zoomed in portion. So I've gone down to the atomic size. When zinc is in contact with a metal ion, something else in solution below it, that means these zinc atoms are going to be going into solution and losing electrons. As they lose electrons, they now have a charge. And those electrons that are lost are now traveling up the zinc, traveling along this wire, coming all the way back down in here, and then grabbing these ions in solution and depositing them, as solid atoms. It's effectively removing their charge as they gain those electrons. So that means on this side, this electrode, when it's losing those electrons, is getting smaller. Those ions are going into solution. And this electrode on this side, as it's gaining those electrons, is getting bigger. I've also just kind of given you a hint there, but this side, because we're losing electrons, this is your oxidation half cell, and this is your reduction half cell. It's gaining those electrons. In chemistry, we use two fancy words to kind of talk about the electrodes present in this situation. We use anode and cathode. To remember which one's which, we use this acronym. Well, it's not really an acronym, I guess it kind of is. Anox red cat. So the anode happens at oxidation. So here's my anode, this electrode. And then red cat, reduction, happens at the cathode. This side's reduction, here's my electrode. That would be identified as the cathode. To calculate how much electrical potential we have here, or calculating standard cell potential, we need to jump into net ionic equations and write overall chemical equations. I've done that here to kind of save us some time. What I've done is I've taken my original equation, I've pulled out my net ionic equation, and then I pulled out my half reactions. We did this previously, so hopefully that's not a big jump for you guys. These values here come from our standard reduction potential chart. That is table D in your packet. So I'm looking up these half reactions on that chart. When I look up those half reactions on that chart, I get certain values. We're going to use these values to calculate our standard cell potential. Now, the chart itself is labeled as the standard reduction potential chart. So my reduction value is the value right on the chart. And you guys could look that up and find negative 0.25 volts. However, since this is oxidation, the value on the chart, I need to switch the sign because that is a standard reduction potential chart, and that is oxidation. So it goes from negative to positive. To calculate our cell potential, we use this equation shown in purple. We basically add our two standard reduction potentials together, and I get our total amount of volts present. So here I'm going to be adding this value and this value shown here, and that means I'm producing 0.51 volts when I hook up these chemicals in this orientation. Naturally occurs, light bulb turns on. It's a spontaneous event. Oh, how do I know it's a spontaneous event? Well, the more positive this, jump back. If your voltage is positive, it is spontaneous. It'll actually just happen on its own. Now, a couple other things about this standard reduction potential chart. The more positive on the standard reduction potential chart, the more likely a substance is to be reduced. So, the very positive values at the very, very top, those are more likely to be reduced. The ones that are negative are more likely to be oxidized. And then I would have to switch the sign when I'm adding them together because it is a standard reduction potential chart. That's kind of what that means. We also have these cells called electrolytic cells. Now, electrolytic cells have a major difference in that they're driven by a battery. So galvanic and voltaic cells, these happen as a spontaneous event due to the difference in the pull of electrons from the atoms present. Some atoms really have a great pull of electrons, high electronegative values, some do not. That is a spontaneous event. That's the example we just showed. These just occur. If I were to hook up everything in this case, you guys should be able to solve for positive 2.27 volts. You have all the components necessary. You have the identities of the electrodes, the identities of the ions in solution. There's a salt bridge present. All that happens from that. Your goal, and I hope you could do it anyway, is to calculate the number of volts present. On this side, if we look at it, it's the exact mirror image of the galvanic cell. So an electrolytic cell is driven by a battery. The battery forces the movement of electrons. So the negative component of the battery is always the one you want to pay attention to. That's where the electrons are pumped out of the battery. So if I'm forcing electrons in this direction, that means this is a non-spontaneous event. And this is actually the reverse of this spontaneous event. It's driven by a battery. So that's what we mean by an electrolytic cell, the actions caused by the battery. When we get to electroplating, then it'll make a little bit more sense. Electrolysis. So if I don't have them separate, if I have it something in solution, I can have electrolysis occur with the use of a battery. In this case, we have the electrolysis of water. Electrolysis always has to do with water, so I don't know why I mentioned that, but that's fine. We're going to have a container. Here's my container. I'm going to put 2 electrodes in my container. I'm going to hook it up to a battery. If I just hook it up to a battery, I'm going to start seeing some bubbles present. The bubbles are going to be hydrogen gas and oxygen gas. I'm taking water and I'm splitting it with the use of electricity. That's electrolysis. Here it is. If I look at my oxidation numbers, I could realize that I have 2 half reactions occurring, oxidation and reduction. All right, which one's which? Let's take a look. Hydrogen's going from positive 1 to 0. That is a reduction in its oxidation number. So the reduction would happen at the cathode, located here, and that would be the hydrogen gas. My other oxidation numbers, I have a -2 to a 0. It's oxidation. Oxidation happens at the anode. Here it is. I would have oxygen gas present. I also have a little note here, ×2. Well, why do I have a ×2 there? Oh, so if we look at our overall chemical equation, for every time this occurs, I'm going to have double the amount of hydrogen compared to the amount of oxygen produced. So I would have double the amount of gas present. That's electrolysis. That's how it works. Electroplating. So you can use redox reactions or the use of a battery to plate metals with other metals. We call that electroplating. Cover a metal with a thin layer of another metal. This happens a lot with jewelry. If you have like an iron ring, like you do right here, you could plate it in gold. And then you could sell it as a gold ring. And people would think it's a solid gold ring, but be aware, it could just be electroplated with gold. All right, let's take a look at how this happens. So here we go. We have some gold, and we have an iron ring. I'll make this a little bit more narrow to make sure this is just your iron ring. I also have gold ions in solution because I have some gold 3 chloride. Now, if I hook this up to a battery, that means the electrons are going to be pumped in this direction. I'm going to have a lot of electrons here. Those electrons are going to grab onto these metal ions in solution and deposit them as gold atoms. You're removing the charge as you add on electrons. So these would now be atoms of gold that have been plated on my iron ring. That's how that works. Actions driven by the battery. Cool. For our half oxidation and half reduction reactions. Oxidation, loss of electrons. Where's the loss of electrons happening? Oh, so electrons are coming from this direction. Where are they coming from? They're coming from the battery, but also the battery is connected to this gold. So this gold, these individual atoms are losing electrons, and as they lose electrons, that means they're joining the solution as gold ions. So for my half oxidation reaction, my solid gold is turning into gold ions. The difference in my oxidation numbers from +3 to 0, give me my 3 electrons present. Half reduction. Reduction is happening here. These ions were deposited now as solid gold. Where did they get the electrons from? Well, they got them from the battery. So my half reduction reaction, my gold ion is combining with 3 electrons and turning into solid gold. Boy, that net ionic equation looks like a mess, but it is accurate. Accurate? Oh boy, that's a tough word right now. Anyway, because it's driven by the battery. So gold metal is reacting with gold ions to turn into gold ions and gold metal. That looks really weird, but that's how gold plating works. Anyway, that is that, and I bid you adieu.